Welcome back to ECE 220. Day before no class. Try to remember not to show up tomorrow. We're not having class here. Next Friday we will not have class again, and if you're in that particular section of Group A, though, be sure and show up for your lab on Friday afternoon. Those will be happening. Lab number, what are we on? Lab number 4 is next week. Tomorrow, no class. Group A, your pre-lab, getting you ready for lab number 4. That's due Saturday of this weekend. There will be an exam number 3 review session the next time we meet in this classroom on Monday. Monday we will, and if you have, I haven't set that up. I'll try to remember to give you sort of a way to submit questions if you have questions about exam number 3. If you've been looking at practice exams and say, hey, can you talk about this problem during the review session? Or do you guys have right now a favorite exam you want me to focus on during the review session? We only have about 100 problems in the example exams, so I thought I might just select one exam and work through it to give us a mix of the types of exams and not focus too much on one particular type. That's the strategy for exam number 3. So if you have a favorite practice exam, let me know, and maybe that's what I will use on Monday. But I would probably need a little lead time. I wouldn't want to try that necessarily with you handing me the exam 5 minutes. I want to kind of have things displayed and displayable so we can work through those. Homework 10 is due next week, and that's the RL and RC circuits material. Group B next week, your lab report for lab number 3 is due, and you also will have a pre-lab due the following Saturday, a week from this Saturday. And again, there's our exam. Exam number 3 is a week from today. So it looks like it's about normal. We have about half of the class here. You'll double in size, so we'll do the same strategy for that we've done for the first 2 as far as seating, etc. The goals today, let's remind ourselves of where we're at. We're in Chapter 8. We're talking about RLC circuits. Was there a question about announcements? Okay. How many extra credit questions are we getting on the exam? That's a good question. I have no clue right now. So you better show up next week, maybe even after, I don't know. We need to, I guess, distribute or get your input on some of those extra credit questions. But stay tuned for that. Extra credit for exam number 3. Where was I? Oh, we're in Chapter 8, parallel RLC circuits. Chapter 8 is RLC circuits, second order circuits. We are right now talking about the parallel version of that. I want to remind ourselves of what we ended up with. Then we will look at the different kinds of solutions that we can actually have based on the numerical values that we are confronted with for the R, the L, and the C. We can now have different types of solution structures based on the combinations of R, L, and C. And that is all based on essentially solving a quadratic equation. And we'll be able to find potentially complex solutions to that, and that gives rise to certain structural behavior of our solution. Then we'll work through a solution. I don't think we'll get all the way through, but we do have 3 different types. We have underdamped. That means that they're shaking. That means we have imaginary components to our complex roots. If I say we have complex roots, that could still be S equal minus 1 and let's say S sub 1 equal minus 1 and S sub 2 equal minus 6. Their imaginary component is just 0. But if we had that, that's actually in the over-damped case. If we have two real unequal roots for our quadratic equation solution, we're then in the over-damped. And I'll try to give you different ways of thinking about this. Underdamped means we have shaking or sines and cosines that are exponentially damped. That's the underdamped. Critically damped means we have two real equal values for the solution of that quadratic, and overdamped means we have two real unequal values for our solution. That will all start, I think, making sense as we work through. Let me quickly read you this story that we went through last time. Here's our circuit. Here's our parallel RLC circuit. We can write a KCL, and we have the three different currents out of the top node summing to 0. We can then write those in terms of our state variables being inductor current, capacitor voltage, and we end up with VC over R being the resistor's current, plus I sub L, the inductor's current, plus ICE, which gives us C dV dt for the capacitor's current. We can then rely on Eli. We would prefer not to have too many state variables floating around. For this second order, we can actually substitute or get rid of one of those in terms of the other. If we look at Eli, here I'm saying I'm using the fact that all three of these circuit elements are in parallel. That's why I'm able to say what I'm saying here, that V sub L is equal to V sub C. This is not true in general. We don't always have V sub L equal to V sub C, but in this case with the parallel RLC we do. And now we can rewrite V sub C as L di dt, since V sub C is the same as V sub L. So we can use Eli to replace V sub C in this differential equation above. And doing that, if we simply plug in L di dt, I being the inductor current, for V sub C, we now end up with this second order differential equation. And we're assuming all of our circuit elements are time invariant or constant. That allows us then to slide those outside of our derivative operation, rearranging that equation in terms of highest derivatives on the left, and then we just work our way down. We have the second derivative of the inductor current with respect to time, weighted by LC, plus L over R times the first derivative, plus I sub L. And again, that's just all coming from our KCL equation in the parallel RLC circuit. A more standard form might be that we now replace or multiply everything by 1 over LC and make the leading coefficient of our highest derivative 1. When you get into subsequent classes, they may say, oh, we have a monic polynomial. Monic 1, that just means they've normalized their polynomial to have the leading coefficient, the coefficient of the highest power of the variable, let's say it's s squared, they've normalized it to 1. You now have a monic polynomial. You've factored everything out, and now you have an s squared plus something s plus something else. That's what we're getting ready for if we wanted to in this case, but now we're simply putting all of the constants, we're putting those in the lower order terms in terms of I sub L. And this is now our second order differential equation, which we anticipated because we had two energy storage devices in that RLC circuit. We want to find now, so that's kind of, well, we're still going through the review. We want to find a solution for I sub L. Can we now find an expression for the current in our inductor that will satisfy that homogeneous second order differential equation? And that second order differential equation is linear and it's time invariant. The coefficients are not functions of time. The R's and the L's and the C's are constant. So you'll hear this referred to many different ways. Here I've just said it's a second order differential equation. But if we now assume our inductor current is A e to the st, S could be a complex number, A could even be complex, they're just unknown or yet to be determined. We can differentiate that. That exponential is fairly straightforward to differentiate. And when we differentiate it twice, we have an s squared popping out in front. When we differentiate it once, we have an s. Substituting those derivatives in for, or using those derivatives on I sub L allows us to rewrite that second order differential equation in terms of our suggested solution, A e to the st. Those three terms share a common term, A e to the st. We can factor that out, and everything still has to equal 0. But if we want a non-trivial solution, all that means is we really want A e to the st to be something other than 0. We don't want to have that. All we need is that product to equal 0 and we're done. Or we have our answers, or getting close to our answers. Setting A e to the st gets us nowhere in terms of a solution. That just says your solution is 0. Yes, 0 current will satisfy that second order differential equation. We don't want that. We want a non-trivial solution. So we're assuming that A e to the st is not equal to 0. We can divide it out. And here's where we ended up, I think, last time with equation 8.3 in the textbook. This is the characteristic equation of, we started with our parallel RLC circuit, and it's going to be different when we start with a series RLC circuit. We'll end up with a different second order equation. That's why we're saying this is the characteristic equation of a parallel RLC circuit. So once you see a parallel RLC circuit, boom, you can immediately write down this second order. You don't have to go through what we just reviewed. Now I hope you have a better feel again for where that comes from. But now what you'll focus on, since we have limited time, is saying, oh, I have a parallel RLC circuit. Let me find the equivalent resistance, inductance, and capacitance. I now know what the solution has to, or what the exponents need to be in order to satisfy that particular RLC circuit. The S's have to satisfy that quadratic, the S values that we find. And we know from previous math experience that when we have a quadratic, it could end up with complex roots. Let's now just quickly find those roots in terms of R, L, and C. And here all I've done is I've just assumed that we might have this generic quadratic as squared plus bs plus c, and now we know that s, the two values of that are minus b plus and minus the square root of b squared minus 4ac over 2a. And associating a, b, and c, lowercase c, that's not a capacitor in that generic little a s squared plus little b s plus little c equal to 0. now you associate the appropriate lowercase a, b's, and c's in this structure, and you can now determine an expression, a functional form, for the different solutions, S sub 1 and S sub 2, for that quadratic expression in terms of the r's, the l's, and the c's. Now if we push that 2 in the denominator, here's just a little algebra. If we push the 2 from the denominator up into the other terms, we can see that the first term is this minus 1 over 2rc. Plus or minus, we put a 2 underneath a radical. That now needs to be 4. It's now dividing everything in the discriminant by 4, and we had a 4 sitting up on the rightmost term to begin with. We clear the 4's, or we put the 4 inside the square. So now we see this 1 over 2rc appearing in two different locations in that expression. And that's now, again, what you could immediately write down if you say, oh, I have a parallel RLC circuit. I know my R, L, and C. Let me find the values of S that will give me the solution structure to solve this parallel RLC circuit. You can now plug them into this formula in the appropriate locations. Those values for S sub 1 and S sub 2 depend on R, L, and C. That's, I think, clear from the expression. What if we went ahead and went back to where we were talking about this tank with water sloshing around, or a mass spring system? It will just keep going between potential and kinetic. It'll just keep going back and forth. Well, that's what we're doing in our tank circuit, where we don't have any resistance, where we extract or pull the resistor out of that parallel combination. What happens in this expression for the roots? If we let R go to 0, do you see that the first two terms vanish? All we're left with is plus and minus the square root of minus 1 over LC. That's all I'm writing down here, but we're in the know. We know how to play with the square root of minus 1. We know how to work with complex numbers. We just give it a J. So now those roots for this tank circuit are purely imaginary. They are plus and minus J times 1 over the square root of LC, or the square root of 1 over LC, however you want to think about it or write it. Those are now our roots that satisfy the quadratic when we have no resistance, when the resistance is gone to infinity in the RLC circuit, parallel RLC. And what did we learn? I already gave this away. In the tank circuit, with R going to infinity, when we extract that resistor, the circuit just wants to oscillate. It just wants to be a cosine with a given frequency, and now we know the frequency. It's 1 over the square root of LC. There's no damping, and now you're going to see me wanting to put this into a figure or a complex plane. Now we can identify where those two values of S are, S sub 1 and S sub 2, in our complex plane, where omega naught, the resonant frequency that is displayed by the values of L and C in that tank circuit, they now live on the imaginary axis. Remember our complex plane. The real line is the horizontal direction. The imaginary component is the vertical direction. If we have no real component, we're living on the imaginary axis. And these roots are always appearing in conjugate pairs. So if you give me a j omega naught, I know that I'm going to have a minus j omega naught because it's coming from a real circuit, and my real circuit has real coefficients. So if I end up with a complex root, I have to have its conjugate. Here, the real part of that root doesn't exist, so we are at j omega naught and minus j omega naught. And this we could say, okay, this one I'm going to say is my S1, and this location is my S2. And in subsequent classes, you're going to call these modes, or these values of S that satisfy your differential equation. Those are coming from the denominator of a transfer function expression, or a ratio of polynomials. And those in the denominator will be poles, and you'll draw those with x's in the complex plane. So I'm just going to indicate these locations with x's so that it will be consistent with subsequent material that you have moving forward. What happens when we say, well, we're not always going to be living with tank circuits, but having radios is nice, and that's why we can use a tank circuit to tune the dial if you're wanting to try to listen to a game or something. Does anybody even use a radio anymore? I see things sticking out of people's ears, but I don't know if they're tuned into a radio or not. But you could tune a radio and listen, and now you have a feel for how it could be done. You could create a tank circuit so that when the frequency is just right, that's the only signal, that station is the only frequency that you're picking up so that you can listen to it. Now let's go back, or move forward, however you want to think about it. Let's introduce resistance into this parallel RLC, and now we have the full-blown structure back with us. We have the R's present, and the textbook likes to introduce some more notation, so let me be consistent with the textbook. Let's introduce an alpha. That's going to be defined as 1 over 2RC. And now we can simply refer to these roots. When you plug all these RLs and C's into your calculator, you're going to probably just get a number. And it may be complex. Well, now you can figure out how that arose, or how that came into being. Alpha is now 1 over 2RC. That's the Nepper frequency. I'll probably just say it's the damping. That's with positive resistance. That's how far into the left half plane. I'm using terms that we haven't talked about, but that's how far into the left side of the complex plane we are. That's the negative real part. Omega naught, we already have seen that. That's the resonant frequency, and actually it has units of radians per second, so they become more descriptive and say that's the resonant radian frequency, omega naught. Now, what S ends up giving us for S sub 1 and S sub 2 depends obviously on what's happening underneath that radical. What's happening with our discriminant? It could be positive. Then we're pretty comfortable with that. That difference of alpha squared and omega squared could be negative. Then we keep our j around. That now we have complex roots, but the different values of S sub 1 and S sub 2 depend on what's underneath that radical. What is our discriminant? Alpha squared minus omega squared. If what's underneath that square root sign is positive, if we are calculating this, we found our Nepper frequency, 1 over 2RC, and we found our natural frequency, 1 over the square root of LC. We square them and compare them. we say, oh, alpha squared minus omega squared is greater than 0. Or alpha squared is greater than omega 0 squared. What was alpha called? What were we calling alpha? The Neper frequency, or the damping. Let me just say this is now our damping. This omega naught is our natural frequency, or I should say resonant frequency to be consistent with the book. And do you see that the damping is over in size than the resonant frequency? So you could think of this as, oh, our damping is bigger than our resonant frequency, so it's over. That's where the over damped you could think of is coming from. You have more damping relative to the resonant frequency. If you're trying to keep this in your head clear, I think the next picture will help. But here, if we have more damping than we have resonant frequency value, then we're going to be saying we have an overdamped second order circuit or system. And that will give rise to two real unequal roots. If you look at this and you say, oh, underneath that radical is a positive number, the square root of that's going to give us a nice number, and we're just going to add and subtract that to minus alpha. So our S sub 1 and 2 will be real. They'll just be different in value. What if we go the other way, and now we say, oh, alpha squared minus omega squared is actually negative? Based on these alphas and omega squares all depend on R, L, and C. If that's the case, then the alpha squared is under or lower in value than the omega naught squared, so it's underdamped. And we end up with two complex conjugate roots, because we have the plus and minus, and we have a j square root of whatever that difference was. This one's, I mean, it's common in a textbook setting. In real life, it's not very common. But you could have the damping equaling the resonant frequency. Or what's underneath that square root is 0. You have now alpha squared equal to omega 0 squared, and we'll call that the critically damped case. And if that's the case, we now have two real equal roots. We have minus alpha plus and minus 0. And we needed S sub 1 and an S sub 2. So both S sub 1 and S sub 2 are minus alpha. Oh, this is such a colorful chart. I spent 3 hours trying to create this, so appreciate it. I had to find another color, and since it's October, the last day in October, I thought orange was appropriate. Orange is now the overdamped case, and it's a little bit hard to see, and if you print this out on a laser printer without color, you're not going to catch all of this information that I'm trying to encode in this figure. But we know where the no damping case comes into play. That's our tank circuit. That's the red. That's J omega naught and minus J omega naught. What color do I want to use to go? Underdamped is the blue. That underdamped means that we have conjugate roots, complex conjugate roots. So the underdamped is here in the lower half plane, and its twin in the upper half plane. The critically damped are the two real equal poles, and those are on top of each other. Can you see that? Do your glasses that you're wearing show you that those are right on top? I'm actually staggering them so that you realize there's two. But they're, in fact, right on top of each other, and they're real. They're on top of the real axis. This horizontal is the real axis. This is still the complex plane. And this is the imaginary. And then the overdamped, maybe I don't want those lines crossing. So let me, but it has somebody else closer to the origin. You have two orange roots. The way to think of this, maybe, you come up with your own way to visualize this, but let's say we're in the tank. That didn't sound right, but the tank circuit. We now have our tank circuit. We're on the imaginary axis. We now start to increase damping, introduce the R. If we kept omega naught the same, do you see that we would stay the same distance away from the origin? Omega naught is our resonant frequency, or the natural frequency, and now if we increase our damping, we're actually swinging around and having less vertical distance. The more vertical distance we have, the faster our oscillating frequency. As that blue X, or value of S, goes from purely imaginary all the way down to critically damped or real, do you see that the real component is getting bigger than the imaginary component? And the imaginary component determines our, here's another word, damped frequency. I had a P in there. It was damped frequency. D-A-M-P-E-D. Damped. I know you're thinking it's some other kind of frequency, but it's the damped frequency. Have too many frequencies. We have a Neper frequency. We have a resonant frequency. Now we have a damped frequency, and that damped frequency is going to be in the argument of cosine, and we'll subscript it with a D, omega sub d t. So we have a damped frequency in addition to our resonant frequency. And as we increase the R, we get to critical, and then they actually split, and they just, one goes towards the origin and one goes off to minus infinity in terms of our two real unequal poles. That's how you can sort of think of this diagram in terms of how do these different combinations of S sub 1 and S sub 2, how do they arise, or how do they sort of work as a solution to this quadratic equation. That's the way to be maybe thinking about those. A picture to help you keep track of these frequencies. Resonant frequency, which one is that? Give me a color. It's red. Yes? If we now had a set of S's that had complex parts or imaginary components to them, that imaginary component would be our damped frequency. That's the blue. If we had two real unequal, then it's orange, and we're on the real line. Let's now work through putting this now together and moving a little bit further. You're going, come on already, I'm tired. Let's just give me the solution. Let's now figure out, let's determine a solution to a particular parallel RLC circuit. We know that it satisfies this second order differential equation. if you plugged in an a sub 1 e to the s sub 1 t, one of your roots, into that, it would satisfy that. If you substituted a sub 2 e to the s sub 2t, it would also satisfy that, irrespective of determining a sub 1 and a sub 2. S sub 1 and S sub 2 were determined such that they would satisfy that differential equation because they were giving us the solutions to that quadratic equation. Well, if they both work, let's take a linear combination. Let's just add them together and say, okay, let's now say that our current I sub L that will satisfy that second order differential equation is a linear combination of these two modes. The mode is e to the s sub 1t. And what that mode is depends on s sub 1. If it's purely imaginary, it's just a cosine. If it's real, then it's exponential decay. If it's complex conjugate pairs, then it's a exponentially damped cosine expression. We'll get there. Let's now suppose in this RLC circuit that somebody says, oh, the initial value at time 0 for the inductor current is 2 amps. And let's say that the voltage across the capacitor is 1 volt. Also, they're giving us particular values for R, L, and C. Let's say that R is 1/8, L is 1/12, and C is 1. What's our first step? First, we've identified that it's a parallel RLC circuit. Now we need to use equation 8.3, which is going to allow us to solve for the roots S sub 1 and S sub 2 for that parallel RLC circuit. Do you remember what that was? S sub 1, or let's say just S sub 1 and 2. Let's do them together. We'll just keep the plus and minus. That was minus 1 over 2, R, which was 1/8, C, which was 1. That was our Neper frequency. Then we had a plus or minus the square root of that expression there, the alpha. That's what this is, and we can clean that up. We now have a 1 over 1/4, so that now says we have alpha squared. 4 is alpha. Now we square it, and what is, we subtract omega naught squared. And omega naught squared was 1 over LC. That's what we're putting here. And C is 1. Now we can compute our roots, S sub 1 and S sub 2. S sub 1 and 2, we have a minus 4 for the first term, plus or minus the square root of 16 minus 12. What case are we in? Are we in the underdamped, purely oscillatory, overdamped, or critically damped? Which case are we, where are we living on the complex S-plane with these x's? They're on the negative real axis, aren't they? And they're real unequal. This is now our overdamped scenario. Let's now assume a solution for I sub L of t. This is now going to be A1 times e to the s1, but we already know s1, that's minus 2 times t, plus a sub 2 e to the minus 6t. Now we simply need to find a sub 1 and a sub 2. You could be thinking of this as if now you have, oh, here's the complex plane. I'm going to be calling it the S plane because that's how we've labeled our values, but this is our complex plane. We now have one pole at minus 2, or a root, and another one at minus 6. So this one is there, and that one is giving us that. How do we find a sub 1 and a sub 2? Do we have any information to try to find a sub 1 and a sub 2? We have a parallel RLC circuit, and I've given you this information. Have I given you enough information to start finding I sub L of t, a sub 1 and a sub 2? Well, we have I sub L at time 0 plus. We should be able to use that because we've assumed a structure for I sub L. We now know, or we can use the fact that we know this. That was given. Now we can say, oh, if that's the case, then I sub L of 0, which is 2, is A1. E to the 0 is 1, plus a sub 2, e to the 0 again. So now we have a1 plus a2 equaling 2, using that one initial condition. We were given a second initial condition, and that was the capacitor voltage. But this is a parallel RLC circuit. V sub C of 0 plus is the same as V sub L of 0 plus. And remember Eli? Eli says that V sub L is equal to L di sub L dt. Or now we can say this is L di sub L at 0 plus dt. Now we can find the initial condition on that derivative of our current, that first derivative of our current. We know that L di dt is, I think, 1. Didn't we say the initial value on our capacitor voltage was 1? And we know L, that was 1 over 12. We were given that. We were given this. We can now solve for di sub L at 0 plus. Is that equal to 12? That was now 1 divided by 1 over 12. Or 1 divided by L. And if we know this structure for I sub L, we can differentiate that. A1 and A2 are not functions of time. Those are constants. Help me out here. Let's differentiate this I sub L of t. Derivative of I sub L of t is minus 2 a sub 1 e to the 2t minus 6 a sub 2 e to the minus 6t And we now know, or we can evaluate that at 0. And from above, we know that that's equal to 12. Now we have this equation, and we have this equation. Two equations in the two unknowns, A1 and A2, we can solve those. We know that A1 plus A2 was equal to 2. And we know minus 2A1 minus 6A2 is equal to 12. If I now clean this, well, if I convert this, if I multiply this first one by 2, and now I can add those and get rid of the a sub 1. This is just a way to solve that. You could plug it into a matrix equation if you wanted and invert the matrix. It's just two equations in two unknowns. But now I have, hopefully, minus 4a2 is equal to, I'm just adding these, 16. Or I now know a sub 2 is minus 4, and a sub 1 was 2 minus a sub 2 from the very first equation. Or a sub 1 is now 6. Now I know what my inductor current is that satisfies that parallel RLC circuit. I now know that I sub L of t is equal to A1, which is 6, e to the minus 2t, that was e to the s sub 1t, minus or plus a sub 2, which is minus 4, e to the s sub 2t, do you see what that looks like as a function of I, or a function of t, what our current is? It's a couple of exponentials. Are they exponentially damped at the same amount? You guys now know how to sort of think about this. You have two different exponentials. They each have their own time constant. And what can we tell about, or what can we think about when we know we have a time constant? And these are all decaying exponentials. They have negative exponents. We have a 6, if I said sketch 6e to the minus 2t, you could do that. Let's say this is 6. Now what do I do? If I want to just sketch 6e to the minus 2t, do I have any hope of being close to reality with my sketch? When will I no longer see 6e to the minus 2t effectively? All right, what's the time constant of the term 6e to the minus 2t? What is tau 1? It's the value of time, t, that causes that exponent to be 1. So if you now said, oh, 2t equals 1, what's t? That's tau 1. Oh, that's 1/2. This now has a time constant of 1/2. So in 5 of those, in 5 over 2, or in 2.5 units of time, this term is basically gone. Tau 1 is 1/2. So now we could come over here and we could just start labeling tick marks. Here's 1/2. Here's 1. Here's 2. Here's 5 over 2. At 1/2, we're at 37% of where we started. Let's say that's there. Here we're about 15%. Now do you see how we can and by the time we get to 5 tau, we're done. What about the next piece? What's its time constant? It's the value of t that causes that expression to be 1. So that's 1/6. Is this exponential faster or slower than the previous one? Now in 5/6 of a time interval, this is gone. This is faster, isn't it? And it's starting actually at -4. So now by the time it gets to 5/6, which that's a terrible sketch, but it's looking like that. And what do we know? We now know that if we combine those, 4 and 6 and -4, we're starting at 2. Then what happens? Well, this one goes, it dominates a little bit. By the time we get to 5/6, we're pretty much following this top curve. So that's now what the I sub L of t looks like for this circuit. Parallel RLC circuit. It's an overdamped solution. The next one that we're going to talk about is underdamped. It's now going to be an exponential decaying envelope, and inside that's going to be this cosine waveform. This cosine waveform will exponentially collapse. We'll pick up there on Tuesday. We don't have class tomorrow in class, and Monday will be an exam review for exam number 3.